Hi, my name is Dear Tiagi, and in this video, I'll be going over current and Ohm's law for AP Physics C, Unit 11. So throughout this video, I'll be going over this example with water and the analogy it has with electric circuits to explain these concepts in a more intuitive manner. So to start, the first step for understanding this concept is to start with current. So current, which is given the symbol I and it's a vector quantity, is equal, right? Well, first of all, what is current? Current is defined as the flow or the rate of flow of charge. So in this example, what I have is I have these tubes, right? In this drawing, right, these are tubes, and these tubes, you can put water in them and they flow. And so our current is going to be how fast this water is flowing through our system. So our current is the rate at which the water is flowing. And the water, right, the water is the thing that we call the water. These are the charge carriers which are flowing, right? And so in other words, the water is equal to our electrons, right? Because in a circuit, what's moving are the electrons. And so if we look at our system, right, what's happening is the electrons are moving, right, through the circuit from the negative to the positive, like so. Now you may be saying, okay, does that mean the direction is from negative to positive? No. So for current, right, it's a vector, right? The direction for current is known as the conventional direction. And in other words, it's also sometimes called conventional current because it follows the conventional direction that was established, a long time ago. And so in actuality, right, while the electrons are flowing this way, we say that the current is flowing in the opposite direction, right? The current is flowing the direction that positive protons are going, right? Or in other words, the direction of our electric field, right? Because our electric field tells us the direction that the protons or positive charged molecules are going, right? And so the actual formula for I, or for current, charge current, is our dq divided by dt, which makes sense, right? Because this tells us the change in the charge per unit time. And the units, right, it's coulombs per second, which is given the symbol A for amps. And that's our units for charge current. We also now have the concept of charge density, which is given the symbol of J, and it's also a vector quantity. And this is equal to our charge current divided by our area, which should make sense, right? Because that's charge density. So it's the amount of charge current per unit area. Okay? And so the analogy would be, right, if we cut up this wire or if we cut up this piece of tubing and see how fast or how much water was going through that piece of area at that time, right? That would be our charge current or current density. Okay? This is also equal to sigma times electric field. And what the sigma represents, this represents the conductivity of a material, or in other words, how well it conducts. But the more important way of looking at this is that this is equal to our electric field divided by our resistivity. So this is the resistivity of a material. And the relationship is that resistivity is equal to 1 over the conductivity. That's a relationship. Okay? And from this, we get an important idea, right? So with circuits, right, the electrons aren't flowing in a completely empty space, right? There's the actual nucleus of the atoms and stuff, and that kind of slows down the electrons, prevents their flow from occurring. And so the idea here, the way we express that kind of resistance, right, is with the formula resistance, right, resistance for R is equal to our resistivity of material divided by the length of the wire divided by the cross-sectional area of the wire. And this is called our formula for resistance. Okay? And so the idea is, right, if we have a wire of length L, cross-sectional area A, right, there's going to be some kind of resistance based on the resistivity, right, rho of the material. Not P, sorry, I meant rho. Okay? And kind of analogy is, right, if we have like water going down a hill, right, there's going to be some kind of resistance there because there's going to be friction with the ground. And so that friction we can think of as resistance. So resistance can kind of be thought as friction in a way. Oops. Okay? And resistance is given the formula rho, or sorry, the units ohms, and the symbol for ohms is the omega. Right? So our units for resistivity, therefore, are going to be, right, so it's going to be ohms divided by meters. Right, so resistivity is ohms, or sorry, ohms times meters. And then conductivity is going to be ohms meters -1 to the power -1, right? Okay, now let's derive Ohm's law using what we've learned here, right? So we know, right, that from this expression that the electric field is equal to our charge density times our resistivity. So E equals that times that. And we know, right, in a uniform electric field, right, the V is equal to ED. So our voltage is equal to E times our distance. So what I'm going to do is I'm going to plug that in. So say voltage divided by, instead of distance, I'm going to say length because that's what we used before, equals length. And then J is also equal to I divided by A. So I divided by A, rho, right? And so then the L moves over here. So we get V is equal to rho L divided by A times I. You can see that R is equal to that, rho times L divided by A. And so we get our important relationship, or our law, V is equal to IR. And a better way of looking at this is actually I is equal to VR. And what this shows us is, right, is that current, voltage, and resistance are all mutually linked together. And the key idea here is that, as you increase your voltage, right, your current will increase, but as you increase your resistivity, your current decreases. And the analogy for this, right, is you can imagine that if we had some water, right, on top of a hill, then our water flowing down, right, that would be our current, I, right, flowing down. The friction on the slope, that would be our resistivity, R, and then the voltage would be the actual potential we have, gravitational potential from the ground, V, right? And that's kind of the relationship we have here. And if I look back to my example here, right, with the water bucket, what we're doing basically is that this is going to be our battery, right? So our battery provides a voltage, right, because it's providing height, it's providing potential. So our potential, right, providing voltage, potential. These are our wires, which carry our charge, and then we have the I going through. And then you can also think there's going to be some resistance too. So there's resistance probably in the wires through friction. And then here, this water drop, right, when it goes through here, this is our work, right? So this water, right, because it's potential and it goes down to a lower potential, it does work or provides energy. And this work, right, is equal to our change in potential. Okay? And so from here, right, we want to figure out like how much work is actually being done per unit time, which is power, right? And so we know from last unit that work is equal to Q delta V for electric currents in circuits, right? And so if we take the derivative of this with respect to time, dw dt, and we say that V is constant, we get dw dt equals V dq dt, and then we see dw dt is going to be power, right? Because power is work over time, which equals therefore V times I, because dq dt is what we said to be I. So this is another important formula. This tells us that the power for a circuit is equal to V times your current, voltage times your current. And we can also plug in the formula, right, V equals IR into this. So if we plug in for I equals V over R, we get power is equal to V squared over R. Or we can plug in for V equals IR, and we get I squared times R. These are just ways you can represent this kind of same formula. Okay, and again, a visual of in our diagram, right? So if when we're doing resistance, right, the symbol we use for a what we call resistor, right, which gives resistance, is this little zigzag, which shows that the electrons are taking a tough path, which is kind of causing resistance, right? And so the idea is, right, we have a voltage in, a voltage out. The voltage in minus voltage out is equal to our delta V, or V, right? And there's some kind of resistance, and there's some kind of current. And that's what our Ohm's law kind of represents. Okay? So now let's go over resistance, or sorry, resistance in series, resistors in series, and resistors in parallel, just to see the ideas and relationships there. Okay? And then at the end, we'll be going through a resistor network and trying to solve for a lot of things in that resistor network. So if you're taking capacitors, right, the main idea with resistors in series and parallel, right, it's kind of just the opposite. Okay, so if we're in series with resistors, right, so we have a battery here, right, so we have some kind of resistor here and some kind of resistor here. So it's in series because the charges only have one path to go. Call this R1, R2, and call this voltage total. Right, so first thing we know is that our total voltage total, has to equal the voltage here and the voltage here, right? Because we have to be starting at this potential and ending at this potential, so the sum of this potential and this potential has to equal the total potential change. So Vt is equal to V1 plus V2. Right, now we use the fact that I is equal to VR, sorry, V equals IR, right? So I total, the total current times the total resistance, or the equivalent resistance, is equal to I1 R1 plus I2 R2. Right, and the important thing to note here is that I1 and I2 are equal to IT. Right, and the reason why is, if you think about it, right, all the current in the system, right, the current's going through the system, right, from positive to negative, all the current is forced through here, and by conservation of mass and energy, right, we can't lose any of that current. It has to just be keep going through that circuit, and we can't lose it. So our total current is going to equal our current here and our current here. And from that, these all cancel out, and we get that our total equivalent resistance is equal to the sum of our individual resistance in series. Now in parallel, it's a little different, right? It's the opposite. And one thing to note is in capacitance, right? It's the opposite, right? The capacitance, equivalent capacitance is equal to 1 over the capacitances, right? But now we're just adding them, so it's kind of opposite. In parallel, it's going to be, the inverses added together. So parallel, right, let's just draw it quickly. Okay, so this is R1, R2, this is our total, we'll call this one actually IT. Right, so here, our total current has to be equal to each other, right? Because we have current going this way, right? So I total going this way, but then it splits, right? So we have I1 this way, I2 this way, but at the end, they both meet. So I1 goes here, I2 goes here, but they both have to add up to IT, because IT is coming back to the battery. So IT goes in, IT goes out. So therefore, I1 plus I2 have to be summed to IT. Okay? And from there, right, if we say that V is equal, or I equals V over R, then our total voltage divided by total equivalence is equal to voltage 1 over R1 plus voltage 2 over R2. Here, the important idea is that our voltage here, right, because they're all connected to the same wire, and our voltage here, because they're all connected to the same wire, means that they're the same, right? So the voltage here, difference is the same. Voltage here, is difference is the same. Here, is the same too. So here, the important idea is our total voltage is equal to the individual voltages in parallel, like always. Therefore, these cancel out, and so the sum of our 1 over our resistances is equal to, equivalent resistance. 1 over our equivalent resistance is equal to the sum of our individual resistances. Ri, sorry. Okay, and so the important idea here is that it's kind of the opposite of what we had in capacitors. At capacitors, this would be for series, this would be for parallel, but here it's the opposite, and that's kind of what we need to remember with resistors. Okay, so now let's just do a quick resistors problem, right, just to see how we do it, and then we'll be done. Okay, so let's say we had a circuit like so. So we had the battery connected to a resistor here. Then let's say we go into parallel, so we have a resistor here, connect it back over. Actually, let's draw a resistor in there too. Right, and then we have 2 resistors on this branch here. Okay, so call this resistor 1, and this one's going to have 8 ohms. Call this resistor 2, this one's going to have 20 ohms resistance. This is resistor 3, 10 ohms. Resistor 4, this one has 20 ohms. And then resistor 5, this one has 4 ohms. And our total voltage supplied is 48 volts. So the first step, whenever we have a system like this, is to draw our table, right? Because we want to tabulate our numbers in a neat way. Okay, so we're going to label this table with R, resistance, then I, then V, and then P. Right? And the reason why I do it like this is because then R times I is equal to V, I times V is equal to P. So just a clever way or easy way just to tabulate it. Okay, so 1, 2, 3, 4, 5 equivalent. So 1 is 8, 2 is I'll put this here. 20, 3 is 10, 4 is 20, 5 is 4, and we know that our total voltage right supplied is 48. Okay, so first step, right, we can see we need this equivalent capacitance, then find the I's, and then we can find everything else with that. So first, let's find the most complicated section and then figure out our equivalent capacitance of the whole thing. So here and here, right, they're in series, so we add the resistances, so 10 plus 20 is 30, right, so 30 there. Then we have this 30 and this 20 here, so then they're in parallel, so we do the inverses. So 30 times 20 divided by 50 is going to give us 12, so 12, 8, 4, 12 plus 8 is 20, 20 plus 4 is 24, so our equivalent resistance is 24. Therefore, right, V divided by R is going to give us I. So our total equivalent current is 2. Okay? And because we know that this element and this element are in series and they're actual circuit elements, real elements, we know that our current here for 1 is 2. Our current here for 5 is also 2. So our voltage for 1 is 16. Our voltage for 5 is going to be 20. Okay? Did I do something wrong? Oh, sorry, 4 times 2 is 8, not 20. Okay, so we know that, right? And we know that our voltages have to add if they're in series. So this is 16, this is 8. This has to be there for 24, because 16 plus 8 plus 24 is equal to our total voltage, 48. So this element here is going to be equal to 24 voltage, or 24 volts, right? And so we have two elements in parallel, so the voltage difference for both sections is 24 volts. So for 2, that's a real element, so voltage difference is 24 volts. 24 divided by 20 gives us a current of 1.2, right? And because this current is 1.2, we know that in parallel they have to add. So this is 1.2. That means the current from here and here is 0.8. So for both elements, right, the current's going to be the same for elements in series. This can be 0.8, 0.8, because again, they have to sum to 2. We have 2 amps going through here. 1.2 amps go this way. And therefore, to reach 2 amps back here, we have to have what's called 0.8 amps going this way. So there has to be divided like that. All right, so 0.8. This becomes 8. This becomes 16. Right, now we can just figure out the powers. So 32. This is 28.8. 0.8 times 8 is 6.4. 12.8, 16. And if we were to sum these all together, right, we should get, sorry, I think I messed something up, 28.8. Well, we should get that our total is 96, right? And the idea is if we sum these all up together, they should add up to 96. But I might have messed up one of my numbers because I don't think it adds up to that. Oh, no, it does. Never mind. Sorry, it adds to 96. But the idea is, right, these don't add up together numerically. They add up electrically. But these actually add up numerically, right? These ones add up electrically to the equivalents. And these add up numerically. So you can always check your answer by just adding them up together and seeing if it works. And yeah, that's current in Ohm's law and a quick example of a resistor network. Thank you guys all for watching, and I'll see you guys all tomorrow. Bye.